So hello everyone and welcome back to our channel. So this will be a week 6 video. Let me get done with the theory all at once है ना. पहले मैं सारी theory cover कर देता हूँ, then PIQ करवा दूँगा, and if I still have time I will make the practical videos. क्योंकि देखो quiz में तुम्हें at the end quiz में तुम्हें theory को पता होना चाहिए, practical तुम खुद भी कर सकते हो and live coding भी देख सकते हो, है ना, if you really need it that much, and है ना. तो इसलिए मैं let me get done with the theory first so I can get the PIQs and the quiz out of the way, है ना. So let's start with week 6. So first thing in benefit of indirection. Okay. So first thing that we start with is indirection. Okay. So now what is indirection? Indirection in the simplest term is separating interface from implementation. That is separating what you can do from how it is done. Okay. Let's say basically meaning using a middleman. Okay, like for example, if you take an analogy, using a remote to control TV. Okay, so you just need to know what you can do with the TV, right? Okay, like channel up and down, volume up and down, input a channel number. Okay, you do not need to know how the TV is getting to that channel or getting to that volume. Okay, maybe it turns a knob inside it, maybe it uses a switch to on and off, anything, whatever. So you do not need to know how the internal mechanism of the TV works. You just need to know what button I need to press and what it does on the remote. Okay, you are not concerned with the TV for it by itself. Okay, so that's what it means by indirection. Okay, so how we actually use indirection? We use indirection through ADTs, which is abstract data types, that we saw in quiz 1 also, by quiz 1 syllabus also, which separates the public interface from private implementation, promoting reusability. So obviously we show the public interface and not how it is working. For example, we saw in the linked list that we allow the user to add a data node. We allowed the user to add a node with some data, but how the node is being added, the user does not know that and doesn't need to know that. He just needs to know how the linked list works and what he can add. Okay, and he doesn't need to know how the internally it is being added. Okay, so that's all there is to this. Okay, just the recap. Okay, so for example, there is a generic queue which has methods like add element, remove size, which gives an add an element, removes an element, returns the size. So user just needs to know these are the method names and these are what it does. Okay, it does not need to know how it is getting added internally. Okay, and how it is getting removed internally. Okay, he just needs to know remove. If he uses the remove, he will remove the element from the queue. Okay, so now comes the implementation. Okay, how do we implement this? Okay, so there are two ways to implement this: circular array and linked list. Okay, circular array is fixed size array where elements wrap around when reaching the end. Okay, so basically think of it as children standing in a circle holding hands. Okay, so it is a fixed size. You cannot put a single child in somewhere else. Okay, it's a fixed size array. Okay, and on the other hand, there is another implementation, that is linked list, which is a dynamic structure where each node links to the next. Okay, so obviously you can keep increasing it as much as you need. Okay, it can just keep increasing, and if you have double linked list, then it can increase the on the backside also. Okay, so trade-offs. Okay, so obviously if you are selecting one, you are obviously missing out on something. For example, circular array, it is efficient due to fixed storage, but obviously you are getting the limitation on the size. Okay, yeah, the whatever size you set, like 4 1 2 3 4 5 6, let's say 6 people can become one circle. Okay, can be added to one circle. Okay, so you cannot add a 7th. Okay, you need to change this size. Okay, if you change the size, then only you can add 7. Okay, so you are limited by initial size. On the other hand, linked list, it is flexible and grows dynamically. Obviously it is flexible and grows dynamically, but it is higher memory overhead. So if you are working on a system with low memory, then implementing a linked list can be typical. Okay, so yeah, that's how you do it. Now multiple implementation. Okay, let's say I need to implement it more than once, then we might run into some problems, and we'll see how we solve that. Okay, so first thing we can do, the easiest way, that is we define circular array queue, and we give the date, and we define it with basically new circular array, and we define this also. Okay, so what it means is, we have defined it to be a constant. Okay, date circular and new circular array queue. Okay, so now if you want to change the date queue, okay, for example, changing the date queue to a flexible type. Okay, let's say I need date queue to be not be of circular array, but we need date queue to be linked list. Okay, we cannot do that. Okay, we cannot say new linked list here. Okay, because um, it is fixed. Okay, what is fixed? Circular array queue. Circular array basically implements this circular array. Okay, and you can't say that circular array this thing is equal to linked list. Okay, you can't say that. So that's why you cannot change the flexible. Okay, you need to change everyone. Okay, changing date queue to a flexible type, linked list type basically requires updating all reference in the code. Needs to change everything from definition till last usage. Okay, which can be error prone. Obviously, if you are doing that many changes at once, you will cause errors some place or another. At least you are prone to cause. Okay, so basically meaning you can't say that a fixed type is equal to flexible type. You need to change the whole implementation of it. Okay, so how will we get past that? We use interfaces. We define an interface queue and then define subtypes that basically extend this class. And now we have implementation of everything. Okay, queue date data queue. Okay, so now in this case, see the difference. Here we are defining a concrete implementation, that is circular array queue. Here we can define the queue, that is the parent abstract or parent interface. Okay, so what it allows us to do is we can just say new circular array queue, and this becomes a parent sibling parent child relation, and this is fine. Okay, from quiz 1. Okay, parent sibling subtype is fine, parent parent is fine. You remember that. Okay, so it becomes that thing. Okay, so now instead of having to change whole implementation, you can just see a new here. Okay, if I want a date queue which is new, so instead of writing this, I can just say queue. I can say queue date queue string, or queue, let it be date queue date queue is equal to new. Instead of circular array, I can just say linked list date or whatever I want. Okay, like basically instead of string queue here, I write date queue here. Okay, so I did not need to change all the implementation. I just needed to change the instantiation. Lord, never mind, I cannot speak. Here, switching implementations require only updating the instantiation as compared to previous implementation. Basically meaning changing what follows the new word. Okay, basically meaning what follows this decides it. And because we did not use the concrete implementation, we use the interface, parent interface. Okay, but here we use the concrete interface itself. Okay, concrete implementation itself. Okay, so what is a real life analogy? If you wanted to say, let's say concrete implementation is Alex drives blue car. Okay, so if his blue car has broken down, he cannot drive basically. But indirection is Alex drives any pool car. Okay, let's say there is a carpool and Alex can drive anything from there. Okay, let's say he has a garage, for example, and he has tons of cars. Okay, so he can drive any car. If any car is broken down, he can just choose a different one. Okay, that's what we are doing here. If circular array, for example, we cannot use that, or it cannot be used, we can just use linked list queue. But in concrete one, we were not able to do that. Okay, concrete implementation. So now comes a different thing, which is collections. Okay, collections are okay. Before collections, let's say we had some early data structures in Java. Okay, so these are the primitive data structures in Java, which is the vectors, stack, hash table, and bit set. Okay, so what was the problem with them? The problem with the early data structures were that they lacked a unified framework. The absence of common interface led to several challenges. What were the challenges? Code maintenance. Switching from one data structure to another often requires substantial changes throughout the code base. Obviously, vector and bit set are very different between them. Okay, and stack is very different. So if you want to interchange between data structures, it was really messy. Okay, it was not that easy to do. Then there comes a problem of inconsistency. So every data structure has its own method, syntax, and constructors. So every data structure has its own method, syntax, and constructors with no standardization. Okay, everyone had different constructors, different methods. Okay, vector had different methods, stack has a different constructor and different methods for itself, bitset has a different of those. So developers had to remember all the unique functionalities on all the methods. Okay, or they need to keep checking them, okay, before using them, just so that it did not forget, okay, or use different, it's just wrong implementation. Okay, so the fragmented nature of this collection underscored the need of unified framework. Okay, so the collection interface provided that unified framework. Okay, so collection framework is a unified architecture for working with data structures. Okay, it provided three basic and the three most important things that we needed. First is abstraction. Common behaviors of group data are abstracted through interfaces. Okay, so if a lot of things are behaving the same way, we can use a group, we can use an abstract interface to group them, basically we group the common behaviors. Okay, like we did here. Okay, e remove, if we did a default implementation here, so e remove. Okay, remove is here also, here also. Okay, so that's what we are doing. Okay, kind of a really basic example. Okay, we will see examples as we go down. Okay, and second is consistent and predictable API, obviously. So as soon as we standardize it, we know that there is a standard way to do everything. Okay, so we do not need to remember every nuance of everything now. We just need to access the standard API and we can get our work done. And then extensibility. So obviously, and as we have standardized now, then for example, extensibility you can see here. Okay, e remove. Okay, let's say we have a default implementation here. Okay, e remove, but in linked list I want a different behavior of e remove, so I can change the implementation here. Okay, add custom implementation, and also I can add another method that I need for linked list specifically. Okay, so I can add that also here without affecting the code above. Okay, so that's what it means by extensibility. Ability to extend or add custom features or changing the features as intended without needing to make changes to the whole code base. That's what extensibility is. So what are the key interfaces in collection framework? So there are 4 key interfaces in collection framework. First is collection. This is the root interface for all non-key value data structures. Non-key value. Okay, okay, keep this word in mind. Non-key value. Okay, so basically not dictionary. Okay, not dictionary. Okay, non-key value data structures. Okay, then comes list. This represents an ordered collection. For example, array list, linked list. Array list is basically array. Okay, set, which is a collection of unique elements. Then comes queue, which represents a collection designed for holding elements prior to processing. Okay, so queue holds elements that are waiting to be processed. Okay, so you can see the example. We will see the example as we go down. Each interface defines specific behaviors and is implemented by concrete class. So yeah, that's the whole point of interface, right? You just define the methods here. Basically, you just define the methods here, and you how they are implemented is left to the concrete classes. Okay. So methods. Okay, we will see some common methods which are like adding elements, add e, inserts an element into the collection, iteration. This thing which basically will return an iterator to traverse the collection. Okay. Okay. So week 6 is basically Week-6 is basically how you use those. Okay, you will see a lot of things like this. Okay, there's not much to explain in this. You need to try them on your own, or you might have done that already for OP. Okay, so yeah, there's not much to go through. I will just explain everything. Then you go to the live coding or just try these codes on your own. Okay, you have AI thought today. Okay, and I will explain everything, whatever there is to explain. Okay, don't worry about that. Then comes size and emptiness. Okay, so what are the basic methods that we need for a collection? Okay, that's what it is explaining. Okay, so first is obviously if you have a collection, I want to add something to it. Second, I want to traverse it. Okay, third is if I want the size of it, or is it empty or not. Okay, so these are the 3 things, and then comes containment. Okay, containment basically means if something is contained in that. Okay, let's say I want if this object is contained in the collection. Okay, so you can check that. Checks the collection contains a specified element. Okay, then there is this thing contains all. which basically checks if the collection contains all elements of another collection. Basically meaning if there are two collections, then does collection 1 contain all the elements of collection 2? Okay, basically meaning if they are both similar or one is a superset or subset. Okay, that's what it is checking. So yeah, then comes equality. If two collections are equal or not. Equals compares the collection with another object for equality. Okay, then comes additions. Okay, if I want to copy one collection to another, add all. Okay, adds all elements from another collection, which is basically meaning copying. Okay, then at last I would be wanting to remove some elements also, so we can give a specific object to removes a specified element, and remove all, which will basically empty the collection. Okay, removes all elements contained in another collection. Okay, no, so this is remove all elements contained in another collection, basically meaning it will remove the duplicates between this. Okay, so if collection 1 has 2 and 3 and collection 2 has 3, 4, 6, so it will remove the 3. Okay, that's what it means. So while these methods offer extensive functionality, implementing all of them in a concrete class can be labor intensive. Okay, obviously. So see, there are a lot of methods. Okay, I might be needing more methods specific to that concrete class also, so it will become labor intensive to first define all these methods that are there. Okay, and then add custom implementation if needed, and also custom methods if needed. Okay, so the ideal solution might be to provide default implementation in the interface, but this feature of providing default implementation was added to Java later. So earlier, when it was first added, it was labor intensive, but later, since we were able to give default implementation in the interface itself, so we started giving the default implementation of these in the interface itself. So when needed, we can modify that interface based on our needs. Okay, so that then comes abstract implementation. To simplify implementation, Java provides the abstract collection class. Okay, which basically implements the collection interface. Okay, so abstract collection class is nothing but it basically gives the default implementation of these methods defined above. That's all. Okay, so in abstract class, some implementation remain abstract while others can be extended. Okay, then iterator interface. Okay. So iterator interface has three main things, which is has next, checks if there are more elements to iterate over. Well, we saw the iterator interface in week 4. Next, which basically returns the next element in the iteration, and remove basically removes the last element accessed by the iterator. Okay, so here comes the main difference between iterator's remove method is distinct from the collection interface remove method. While the former meaning iterator removes the current element accessed via next. Okay, so basically meaning, let's say we have a linked list. So if my next is positioned here, okay, meaning the cursor is right, the cursor position is here now. So iterator remove, what it will do, it will remove this element. Okay, but in collection remove method, which is defined in collection, we needed to pass a object to it. Okay, basically meaning, let's say E is what I wanted to remove. Okay, and my collection is A all the way up to E and then F. Okay, so no matter where my position is while traversing, if I use the collection remove, then it will just remove this E. Okay, so that's the main difference. Okay, between the collection remove and the iterator remove. Okay, the latter removes a specified object directly from the collection. Okay, so this comes later in notes, but I will explain it here only. If we call remove twice in a row without moving to the next, Java gets confused and throws error because there is no current kid to remove anymore. Okay, I took an analogy to explain that. So kid is from there. Okay, let's say I have a queue. Okay, right now my next is here. Okay, next is here. Okay, so I call remove, and if I call remove, so this kid gets removed. Okay, but my next is still here. Okay, my next is still here. So right now my queue looks like this. Okay, and my next is here, pointer is here. So now if I call remove again, obviously Java will give me an error because there is nothing to remove here. Okay, so between consecutive remove calls, we need a next. Okay, we basically need to get this position to here. Okay, then we can remove that. Okay, this comes later in notes, but I have explained it here also. Okay. There is an example here. Okay, go through these examples on your own. These are really easy. Just what I have explained here basically has next. I will go through one for your help. Okay, so basically we define a collection of strings first. We add these things, then we get an iterator from here. Okay, this thing. So we get an iterator here. We just use the iterator. While iterator dot has next, basically meaning till the collection has elements, it will keep printing the word and moving to the next. Okay, so first thing it goes here. Okay, next is here, so it prints them. Okay, and then moves to the next. Okay, that's how it works. Okay, no, sorry, it returns the next element. Okay, it returns the next element. Next returns the next element in the iteration. Okay, so next first is here. Okay, prints this. It will print there only, right? This has next, obviously, so it will go to the next. Oh, no, it will print this first, then go to the next, and then again check has next, and if true, then it will position that, shift the current position to there and print this. Okay, yeah, that's how it will work. Also, instead of writing the iterator by itself, implicitly writing the iterator, we can just use this for each loop, for each word in words, like we did in Python for each word in words, like that. Okay, so this is the syntax here. It will basically iterate over every word here. Okay, hello world, welcome to Java. It basically uses implicitly uses an iterator. Okay, for each loop. Okay, since having iterator functionality also provides flexibility to write generic function to operate on collection. Okay. So how does it provide that? Because all collections implement the same iterator interface. We can write one function that works with any type of collection. Okay, there is a code here. You can see that from the notes. Okay, basically this thing gives one iterator. Okay, and one print all elements. Okay, it defines one iterator and inside a print all elements. So in the line 1, I cannot mark it here. Okay, just look at the second line. It defines a void print all elements. Okay, I can do this. It defines a void print all elements. Okay, then it defines a iterator and it basically makes the printing statement. Okay, print statement. Okay, so later on when we define different things, apple, banana, cat, dog, red, blue. Okay, so instead of like there is a hash set, this is a hash set, this is array list, and this is linked list. Okay, so instead of writing the iterator again and again, or writing iterators for each, we can just use the one print all elements, and we can just use that for everything. Okay, see the code by yourself once. Okay, it will be pretty clear. Okay, so why it works? Because all collections implement the same iterator interface. Okay, the interface is same. Okay, we can write one function that works with any type of collection. Okay, removing element. This was the line I just explained above. Okay, consecutive calls to remove requires an intermediate call to next, basically meaning remove, then next, then remove again. Okay. Failing to do so results in an illegal state exception, as there is no current element to remove. Okay, I explained everything above. Okay, just go through the examples on your own. Go through them on your own. Implications of iterator or remove. Okay, this is basically going even deeper into that. Okay, into what we just saw. Remove two consecutive elements from a collection if you want to. Then we can not directly call remove twice in succession. Okay, we need a basic next. Basically, we need a next in between that. Okay. I also showed you the difference between the iterator and collection remove. Okay. Now comes, I guess, the most extensive part of this week: concrete collections. Okay. We will go over each interface and we will see the what are the different types of concrete classes we have. Okay. Let me open the page right now so I do not miss anything. Okay. So first is our list interface. Okay. So what we use list for? Ordered collections. If we need an ordered collection, we use the list interface. Okay. Now accessing elements. Okay. If we need to access elements, the list interface gives both options through an iterator. Basically, sequential traversal like in linked list. Okay. If in linked list, you need to traverse the whole list to get to the end. Okay, or whatever element you need. But if it's just a list, you can randomly access that. Okay, so by position random access directly retrieves or manipulates an element at a specified index. Okay, so now obviously if you want to implement random access, then you will have some additional functionalities which are helpful while for random access. Okay, the list iterator interface, which extends iterator, we saw the iterator above, provides additional functionalities specific to ordered collection. Okay, what are the specific functionalities? Add element. So if we use this, it inserts an element before the current index. Okay, then previous, moves to the previous element in the sequence. Okay, then has previous, checks if there are elements before the current position. Okay, pretty easy to understand from the definition. Okay, what this does. Okay, try them on your own. Okay, write a function and just go through them. Okay, the examples are below, don't worry about that. Then comes list interface and random access. Okay, so obviously the random access depends on how you have implemented the list, right? If you have implemented the list as a linked list, random access will be slow, because although you are accessing the fourth element only at index 4 or at node 4, but for the list internally it is still traversing from 0th element, 0th node to the 4th node before returning in the 4th node. Okay, so the linked list implementation is obviously taking more time because it is not random access but a sequential access. Okay, but at the same time, if you have implemented the list as an array, so obviously you can just go to the fourth index and just return that, obviously, so that is faster. Okay, so that's what is written here. If the list is implemented as an array based, so it computes the location of an element at index I using arithmetic operation, so this makes random access efficient. Okay, but at the same time, if it's a linked list implementation, so it requires the traversal of I links to reach the ith element, which makes random access less efficient, obviously, because it is not a random access anymore. From outside perspective, it will still be a random access because you say I need the fourth node and it returns the fourth node, but internally it is actually going to the 0th node, then first, second, third, and fourth, then returning it. Okay, so there are more methods for random access inside a list, which is like add. If we give two parameters, then it inserts a specified element at the specified position in the list. Okay. Get index returns the element at a specified position in this list. List iterator basically returns a list iterator over the elements in this list in proper sequence. Okay, starting in the specified position in the list. Okay, wherever you call that, it iterates from that specific position. Okay, then remove index removes the element in the specified position in this list. Then set replaces the element at the specified position in this list with the specified element, basically meaning if fourth index has E and I do here 4,5, yeah, let's say 4, S, let's say. So now that fourth index S is there. Okay, and it contains this one. Difference between add and set is let's say 1, 2, 3, and then there is nothing, and then 6, 7. So 0, 0, 1, 2, 3. So if I add 3 and then 10, let's say, so it will add the 10 here. Okay, that's how add and set works. Okay, now there comes another interface, which is tagging interface. Tagging interface, random access. So the random access interface is a marker interface used to indicate that a list supports efficient random access. It is basically a way to check if the list or whatever collection you have implements random access or supports random access or not. So how you can check? You can basically use a if statement. If list instance of random access. Okay, so if list is an instance of random access, then it will have some efficient random access strategy, you can implement that. Okay, or if does not support random access, you can have sequential access strategy. Okay, sequential access strategy obviously will work for anything and everything. Okay, then there comes abstract implementations. Okay, so there are two types of implementations, as we all know. There are abstract implementations and there are concrete implementations. So list interface, the abstract implementations are abstract list, which extends abstract collection. Okay, provides default implementation for list methods. Okay. Obviously, there are a lot of methods, as we saw above. We defined some default implementation in the interface itself, so that we do not need to define everything explicitly again and again. Okay, so that's what the abstract implementation do. Okay, we define some default implementation for list methods, and it extends abstract collection. Okay, we saw abstract collection above, just remember that. Then the second one is abstract sequential list, which basically extends this. Okay, this extends abstract list. This is specifically for lists that do not support random access. Okay, if there is a list that do not support random access, like linked list, then this this is useful for those type of list. Okay, now comes concrete implementation. So concrete implementation, there are two main types, but that is linked list and the array list. So extends abstract sequential list. Okay, see, linked list, I just told you that linked list does not support random access. So abstract sequential list is made for those type of list only that do not support random access. So that's why it said that it extends abstract sequential list. So the internal structure. Okay, while working, we need to know what the structure is. Okay, obviously. So we do not need to know the working, but we do need to know how the user does need to know what the structure is. So internal structure is a doubly linked list. What it means that you can traverse or remove in both directions. Okay. So there are some characteristics which are efficient for inserting and removing elements at arbitrary positions. Okay. And inefficient for random access due to traversal requirements, obviously. So if I need the fourth node, then I need to traverse the list till the fourth node and then return it. Okay. Then comes array list. This extends abstract list, as we saw here, abstract list. Okay. So internal structure is dynamically resizable array, obviously. So it basically is an array that we have been using. Okay. So characteristic supports efficient random access. Obviously, we can randomly get any index. And this handles dynamic resizing by allocating larger arrays as needed. Obviously, we can use append. Okay, add. So it just keeps adding more elements to here. Okay, based on how many things we want to add. Okay, so now comes practical considerations. Obviously, whenever you study something like this, you need to think where I will use this. Okay, using random access methods. Okay, while the list interface guarantees the availability of random access methods like get, their efficiency depends on the underlying implementation. Okay, so obviously you can use get in both linked list and array list. Okay, but the how long it will take or how it is being implemented internally will affect the speed. Okay, so if it's an array list, then it will obviously be good at random access and it will return in really less time. Okay, but if it's a linked list, then to get that we need to traverse the whole list till that point. Okay, so each get call may require traversal from the beginning, leading to poor performance in loops. Okay, so it is an example here. See, this is an array list and this is an linked list. Okay, so linked list will obviously be inefficient random access and we will need traversal. Okay, so at the end you are still getting both of these the same output, but in this one it is jumping to 0 directly, then to 1 and to 2. Okay, based on arithmetic operation. But on this linked list implementation, it is not doing that. It is first going to 0, then for 1 also it is going to 0, then to 1, and for index 2 it is going to 0, then to 1, then to 2. Okay, so it requires traversal of the list, linked list completely. Okay, so array list provides efficient random access using arithmetic operations, while linked list requires traversal for each get call, which is less efficient. Okay, okay, so differentiating add methods. So like we saw for the remove method, there's a different differentiation between add methods also. In collection, appends an element to the end of the collection. Okay, so if there is a collection of anything, so add will add elements at the end. Okay, it returns a boolean indicating success. While in list iterator, it inserts an element before the current position. Okay, so if my cursor is here, so it will add an element here. Okay, instead of this array implementation, let me explain you with a linked list implementation. It will be better. So if my next is here, how the add method works here is it will add an element before this current position. Okay, so now it will become like this. Okay, so this is your list iterator add. Okay, returns void as incision always succeeds. Obviously, if there is even if you're at the first position, if you add something, it will get added below before that. Okay, you can see the example here using the list add method, list string list new array list, and you can just add. Okay, appends at the end. Okay, so see system.out list after appending list. Okay, then you are using list iterators add method. Okay, so remember that list iterator. Okay, so list iterator, what it does is first we define it. Okay, get an iterator, then iterator add insert. Okay, so at this point in time we have this. Okay, so where is our position? And obviously one element, so our position is here right now. Okay, so what the iterators add will do, it will add insert before this. Insert that end. Okay, this is how the add method works in list iterator. Okay, list.add e element appends elements to the end, while the iterator add e element inserts elements before the current iterator position. Okay, so just read the summary once. Then comes the set interface. Okay, we have, I guess, 1, 2, 3, 4 or 5 interfaces. Okay, so set interface is basically used when we are particular about duplicate elements. If you want to make sure there are no duplicate elements, we can use the set interface. While the set interface shares the same method signature as the collection interface, behavior is more constrained. Okay, so add element. Okay, adds an element to the set. If the element already exists, the operation has no effect and returns false. Okay, then equals determines equality by comparing contents without considering the order. Okay, so basically this thing compares to sets, and this thing just adds element to the sets. Okay, so what is the purpose of the set interface? So the existence of set interface alongside collection, despite their shared method, is to enforce additional constraints. By explicitly requiring a set, programmers can ensure that there are no duplicate elements and there is an efficient membership check. Okay, so what is this efficient membership check? So unlike ordered collection that require iteration to locate an element, sets optimize this membership testing by, okay, so they have two methods to do this basically. First is hashing, second is balanced search trees. Hashing is mapping values to position using a hash function. For example, every element that I add to my hash map, let's say I divide it by 2. Okay, so let's say I want to add 10, so 10 is divided by 2, which basically means 5. So at 5th index I will add 2. Okay, this is my hash map. Then if you have done PDSA or I guess DBMS also, their hashing and balance search trees both are there. So if you have not done that, you will do that. If you have done that, well and good. Structuring values in a hierarchical manner for efficient lookup, basically asking questions like okay, if greater than 2, search in this. Then if less, if this loop, for example, let's say if this is greater than 2 but less than 1. Okay, so you keep asking questions and keep going on one side. Okay, so that's how you search. Okay, basically meaning you reduce the number of comparisons in by each question. Okay, that's how balanced search trees works in a way. Okay, so abstract set and concrete implementation. Okay, so the abstract implementation is the abstract set only. Okay, so there's only one abstract implementation for this one. Okay, so it gives the default implementation for many set methods, and then comes the concrete implementations. Okay, so the first concrete implementation is the hash set. Okay, don't worry about these things, how to remember them. I have a table at the last. Okay, so the underlying structure for a hash set is an array where values are mapped to position using a hash function. So let's say I have this array and the indexes are 0, 1, 2, 3, 0, 1, 2, 3. Okay, so let's say again I have the division 10 by 2 is equal to 5. So let's say I have by 5. Okay, instead of 2. So now it will be 2. So at 2 second index I will have 5. Okay, so that's how a hash mapping works. Okay, handling collisions. If two values map to the same position, the collision is resolved using strategies like probing or chaining. Okay, probing means let's say I have another. Let's say I have to add 10 again. Okay, let's say I have to add 10 again. So again, if I divide this by 5, it will become as 2. Okay, So now I cannot add, sorry, it will 10. Okay, it will 10 here. 0, 1, 2, 3 and 4. Okay, so I have 10 here. Okay, so obviously if I want to add 10 again, obviously I cannot add 10 again, because this uh, basically hash set is a set which does not allow duplicates, but just for example, because I cannot think of a hash function right now. Okay, so just to show what collision is, I am taking this example. Let's say I add 10 again, so again it will come to second index, but already I have 10. So there are two methods I can do here. So as soon as I see that this place is not empty, I can keep going further down. Okay, and as soon as I find an empty place, I add the 10 there. Okay, this is one way. And second way is chaining. Okay, I add a linked list, I make this as a linked list and add 10 here. Okay, and for, let's say I have to add 10 again, then I will again do this. Okay, this is chaining, this is probing. Okay, membership testing is fast because we saw that hash function determines the position. So if I want to check if 10 is a member, let's say, so I can just divide it by 10 by 5 and say we have 2. Okay, so 2, I can just see that 2 has it. Okay, at 2 I can just jump to the second index directly, and I do not need to traverse 0 and 1. Okay, so that's why it is fast. Okay, this is unordered. The iterator visits elements in an arbitrary order but guarantees that each element is visited exactly once. Okay, this is how you implement a hash set. So adding, we tried to add Java thrice. Okay, Java. Okay, we added second twice. Okay, now adding Java twice results in only one instance in the set. Okay, the order of elements in the hash set is arbitrary. Okay, membership testing, how you add, so 5, 10, 15 you added. Okay, set contains 10. Okay, so it will go to the hash map, it will check the hash value and it will check based on that, like we saw above. Okay, so 10 true, 20 false. Let's say I had the hash function was 10 divided by 2. Okay, so 10 divided by 2 will be 5. So it will go to the fifth index and it will see that yeah, 10 is there, and now it will check for 20. Okay, so 20 divided by 2 is 10. Okay, so now it will go to the 10th index. So at 10th index it will see that 20 is not there. Okay, let's say I have 30. So yeah, so it will go to the 15th index. Okay, it will check. Since 30 is not there, since 20 is not there, it will return false for both of them. 30 is not there, I just explained to you. Then comes another concrete implementation, which is a tree set. Okay, so the hashing allows constant time complexity. Okay, obviously all these functions like dividing or checking any function, it is considered to be a constant time. Okay, now coming from PDSF. So now tree set, same things we will go over. Underlying structure is a binary search tree. Membership testing, it will O of login. Okay, for elements, and then sorted this one is sorted. Okay, the iterator visits elements in ascending order. Okay, remember that. Use cases when ordered set is required. Okay, hash mapping when we don't need a ordered set, but if we need something which does not allow duplicates but also we need it to be ordered, then we use tree set. Okay, this is an example. Okay, if you want to know more about balanced search trees, just search up on Google. Okay, search up on YouTube. You will get tons of videos. Sorted order. So, what are the main things for tree set? Elements are sorted in ascending order using a balanced binary search tree, and this is efficient membership testing because this provides the time complexity of log n complete. Okay, for lookup operations. Okay. This is a table also. You can see we have this table at the end. Okay, so don't worry about that. Now moving on to the queue interface. Okay, so queue interface has an ordered collection designed for holding elements prior to processing. Okay, so before processing we need to have a queue, obviously. Okay, to hold the element that will be processed right now. Okay, so obviously we know that queue is a first in first out. Okay, first so queue is like this. So this guy came first, so he will go also first. Okay, so what are the core methods? First is add. and remove. Okay. Add inserts the specified element in the queue. If the queue is full, this method throws an exception. Remove removes and returns the head of the queue. So as you know, queue interface or queue state structure allows the insertion and addition. Allows in removal from one side only. Okay. So there are some gentler variants. Okay, why do we need gentler variants? Because these methods, what they do is, if for example this throws error, it will crash the operation. Okay, it will basically crash the operation. So to handle errors more gracefully, we use the offer. Okay, so what it does is, it attempts to insert the specified element but returns false if the queue is false. So we can use try, except, or if else block to handle those things. Okay. So poll, what it does is, it retrieves and removes the head of the queue, returning null if the queue is empty. Okay. So what remove does is, it returns the head of the queue. If the head is empty, like the queue is empty, it will give an error. Okay, it will crash the operation. But poll, what it does is, it retrieves the head if the head is there. But if it is empty, then it will just return the null. Okay. So there are other methods also. Inspecting the head element, which basically returns the head of the queue but throws an exception if the queue is empty. Peek returns the head of the queue or null if the queue is empty. Okay. So this is the code example of queue. Okay. Just go through this, really easy. Okay. Try it on your own. Try the method on your own. Okay. These are the methods that were defined above. Okay. Just a quick recap. Then comes the DQ. DQ is the same as queue, just a double-ended queue. Okay. So in queue we were adding behind and removing from front, but in the DQ we can do both things simultaneously from both directions. Okay. So these are the methods for insertion, these are the methods for removal, these are the methods for inspection. Add first inserts the element in front, last at the rear. Offer first attempts to insert, and these are general methods. Okay. These are the general methods. Okay. Poll first removes and returns the front element or null if the DQ is empty. Poll last removes and returns the rear element or null if the DQ is empty. Inspection get first retrieves the front element, throws an exception if the DQ is empty. Just go through them, they are really easy. Just read these lines. There's not much to explain, they are pretty easy to understand. Just read the definition, it is this becomes clear. Okay. Then comes priority queue, which is not really used much, but there are specific scenarios where we need a natural ordering or a custom comparator. Okay. So what the priority queue interface does is, it extends the queue. Okay. So since it extends queue, we can say that it will insert from behind and remove from front. Okay. And orders element. So this is an ordered. Okay. Based on the natural ordering, for example 1, 2, 3. Let's say this is a natural ordering or a custom comparator. Okay. Let's say we have a custom comparator. Let's say high school is less than graduation, is less than PhD, like that. Okay. So this is a custom rule. Okay. So what are the key characteristics? There are two: insertion and removal. Operates similar to the standard queue, but ensures elements are placed based on priority. Okay. Let's say I have another graduate. Okay. So obviously the graduate will be placed based on the position of high school and PhD. Okay. So that's how the natural ordering. Okay. If I have 1, 2, 7, 8, and if I want to add 4, then the 4 will add it here. Okay. That's what it means by based on priority. Remove method retrieves and removes the element with the highest priority. Okay. So here the removal is based on the highest priority. Okay. So PhD will be removed first. Okay. Concrete implementation and linked list. So the linked list class implements both queue and DQ. Okay. So doubly linked list, obviously. So since a linked list, look, think of it like this. Okay, linked list. So if I'm just adding from behind, or if I'm just adding from here and removing from here, then it becomes type of a queue. Or if I'm adding here, adding from behind and removing from front, becomes type of a queue. But if I'm doing both directions simultaneously, then this becomes sort of a DQ. Okay. So the linked list class implements both queue and DQs to provide us with a doubly linked list, so that we can do operations in both directions simultaneously. So what are the key characteristics? Efficient insertion and removal at both ends. Okay. Because this is a doubly linked list. Can function as a queue or DQ. So then comes array DQ. This is another concrete implementation, which provides a circular array implementation of DQ. Okay. So circular array we already know, which is a fixed type. Okay. So what it does, it supports efficient resizing. Okay, so we saw that this was a fixed type, but here we can efficiently resize it, and this is preferred over linked list for stack and queue operation due to lower overhead. Okay, so we saw that circular array is a fixed type, so it will obviously have low memory overhead. Okay, that's why it is preferred over linked list. Okay, then there comes the summary. Then the last one, which is a map interface. So map interface, you already know, which is, it is basically a dictionary in Python. Okay, uh, we saw that collection interface, right? Where it was, see, I told you to remember the one thing, which is the non-key value pairs. Okay, where is the key, where is the key, where is the collection? Okay, so the collection interface contains non-key value. Okay, so for key value pairs we need something. Okay, so that's where the map interface comes into play. Okay, so map interface in Java is designed to handle key value pairs. Okay, enabling efficient data storage and retrieval based on unique keys. So whatever you learned in Python in dictionary applies here too. So key is type for keys, and V is for values. Okay, so get basically retrieves the value associated with the key. Okay, so this will return the value associated with the key. Okay, so if k key has a V value, then it will return the V. Put basically updates or adds a key value pair. Contains key basically and contains value. Just check for the presence of specific keys or values. Okay, it's pretty much clear from the name itself. Okay, so what are the key characteristics? Keys form a set. Each key is unique. Okay, so adding a new value with an existing key overrides the old value. So k let's say contains 1. If I have one more k and I add the 2, so this will get removed and this will stay in the dictionary. Okay, put k key and v value. This line is wrong. It creates a new entry as we saw here. Okay, get basically returns value associated with that key. Okay, this thing. Code example is here. Alice 95, Bob 90. We add two key value pairs and then we retrieve one, and then we use contains. Okay, we use the contains to check if both of these are there. Okay, then comes updating. Okay, get or default returns the value for a key if it exists, otherwise returns a default value. Okay, so let's say I need a default value for something. Okay, that's where it comes into play. Okay, for example, we have a new hash map. We use get or default. Okay, for now we have Alice and Bob. Okay, this example extends from here only. Okay, so right now we have Alice 85, Bob 90. But if I try to search for Charlie, obviously it will not be there. But I am using get or default. So get, it will try to get the key, get the value for key Charlie. But if it does not find the key for key Charlie, it will return the default value, which is 0. Okay, so default score for Charlie 0. We can also use this. There's the it is not like that. We cannot use that. Here we stored the default score in a variable, so now we can use that. Scores dot put Charlie default score plus 10. So now updated score for Charlie becomes 10 because the update default score was 0 and then we added 10 to it, so it becomes 10. Put if absent. Okay, so this is another method which adds a key value pair only if the key is missing. Okay, so right now we have Alice, Bob and Charlie. Let's say I want to add Dave, but I do not know if it is present there or not. So I can use put if absent Dave 50. Okay, score of Dave 50. See, we put if absent Dave 100. We also give this line, but this line has no effect because put if absent returns false because Dave is already there. Okay. Then comes merge, which basically merges to combine the current value with the new value using a specified function. Okay. See the example here. We add Eve 20, then we merge Eve 10 integer sum. Okay, so what it does is it basically does the integer sum of 20 and 10. So 20 plus 10 is basically 30. Okay, so now it will give the updated score for Eve as 30. What is the function here? Sum. Okay, it says combines the current value with the new value using a specified function. That's the function is the sum function here. So how to extract keys and values? Key set basically returns the set of all keys. Values return a collection of all values. Remember this. Set of all keys, collection of all values. Remember this. Entry set returns a set of key value pairs as map entry KV objects. Okay. This type of object will be returned if you use entry set. Okay. How to iterate over a map? So you can iterate using a key set. iterates of the keys and retrieves values using them. Using values, you can directly iterate over the values. Entry set, you can use iterate over key value pairs together. Okay. And at last, using an iterator. Be useful when modifying the map while iterating. If you want to iterate plus modify, then using an iterator makes more sense. Okay. So here are some example: extracting keys using key set, extracting values using this, extracting entries using this. Okay. So see how the outputs are different. Okay, for keys keys, values, and entry set. Okay. Then there comes the concrete implementation. First is hash map. It uses a hash table for storage and it provides fast access but does not guarantee order, just like hash set above. Okay, it's the same principle. So map.entry. Then comes a tree map, which is basically the same as tree set, which basically use balanced search tree, and we saw that that was also sorted in natural or custom order. So this is also sorted in natural or custom order. Then the third comes linked hash map, which is basically a combination of the both. Okay, this maintains insertion order or access order, and it is ideal for implementing least recently used LRU caching. This was in DBMS, I guess. LRU caching. If you know that, well and good. But you do not need to know that for this one. Okay, just remember that it is useful for LRU caching. Okay, this was a table I was referring to. You can see all the concrete implementations here. Okay, you can see all the concrete implementations here. You can see the internal structure of them, if they preserve order, if they allow fast lookup, and any extra features. Okay, so go through the table once. Remember this table. Questions might come. Okay. So that was all for week 6. Go through the notes once. These are really easy. Try to code them on your own. Okay. Go through the examples. These are really simple things. Okay. Watch the live coding, or just go code them yourself. Okay. So and use AI if you are stuck. Okay. I will go through the theory first. Then I will try to get practicals done if I have time. Okay. I have 4 subjects myself, so I can't do everything. Okay. Yeah, so that was all for week 6. Thank you for watching and all the best.